All right, everyone, we'll go ahead and get started, even as people are sauntering in here. So today we're going to be talking about performance as a first-class feature in your .NET applications using NBench. So my name is Stannard, and I'm the founder of NBench. And I'm going to begin our talk today with a little story about how NBench came about and some of the problems we were dealing with on akka.net, which is the other open source project I spend most of my time working on. So philosophically speaking, performance is a feature of your application, just like anything else. So imagine this, you're all developers who have employers who care enough about your career progression and development to send you to a conference like this. You are proud of your work. Would you ever go ahead and ship a feature that you thought was really important and useful to your customers without testing it? Would that be something that you would deem acceptable? And the answer is probably not. Well, what about the performance of our applications? So for instance, if we're shipping a web application, one of the things that can make a really big impact on our end users is how quickly we're able to fulfill a response to a user's request. What would happen if Google, every time you went to go and load it in your browser, took, let's say, 4 seconds to load the home page? Would you keep using it? Probably not, right? You want to switch to something faster. Or how about a cell phone application, so iOS or Android app, that ended up using all of your prepaid bandwidth every month? Would you use that or switch to an alternative that was better designed? You'd probably switch. Or how about a desktop backup application that took 10 hours to back up end to end and used 100% of your CPU while it was running? Would you keep using that, or would you find an alternative? These are all extreme examples, but nonetheless realistic ones of where the performance of an application could make such a negative impact on the end user as to drive them to find an alternative. So the underlying theory here is that performance is a feature of our application just like any other piece of functionality. But what separates it from everything else is how classically difficult it is to assess and test the performance of our code versus the functionality of a feature. When you write a traditional unit test for a feature, you basically have some input and you expect some output to occur, right? And you can basically objectively determine that pretty easily. Well, how do you measure performance? And how does that vary by the type of hardware someone runs? Or what else is happening on the computer at the time you wanted to gather that benchmark data? These are all problems that are actually pretty nasty. And so what I'm going to present you with today is NBench, which is a tool that is designed to help simplify all those problems and make it so programmers can productively manage the performance of their applications without having to write large pieces of infrastructure themselves. So I'm going to begin by sharing a performance story from akka.net. So this is the other big open source project that I work on. I just gave a talk about it the last session here. And it's designed to be a high-performance distributed actor framework. And so that means that we have to have some performance goals around how quickly actors process messages, how quickly they're able to send them over the network, how much memory they use, how quickly they can start and shut down, so forth. These are all things that actually really do matter to our end users, because a lot of them are building applications that have their own real-time response requirements. We have people who are using akka.net for safety-critical systems. Do you think if we had a 4-second GC pause between when someone pressed an all systems stop button and when the machine turned off, that could be a problem? Yeah. So here was the problem that we had. In one patch last year, we rolled this out to our users in production, and we got a bunch of reports back right away saying, hey, my akka.net cluster slowed to a crawl, where I'm getting something like 1/5 of the throughput I used to get. And that's the difference between my system staying up and serving my customers and going down. And so we went ahead and we loosely measured it and realized that we were doing something like 2,400 messages per second, which is terrible. That's not good. And so the problem was, when our team decided to get on it and tackle this problem, the conversation looked a lot like this. One person asking, maybe it's the serializer that's the problem. Then another chimes in, my benchmark shows it's our TCP transport that's the issue. This is probably me in this conversation. My benchmark shows the performance is fine. This user's doing it wrong. Then there's someone else who says, I profiled the code, and it's in the thread pool, I found it. And then we have the one jerk on our team who basically mentioned that Hermione dies in the Deathly Hallows. Yeah, sort of Harry Potter joke. And so the gist of it was that this became this sort of endless conversation where it was like watching dogs chase their tails, except in GitHub comments, where no one was able to have a coherent conversation about the performance of our code because we were all using totally different tools, totally different environments, totally different hardware, totally different benchmarks, totally different instrumentations, and you get it. There was nothing in common at all. It's like a bunch of people shouting in different foreign languages to each other, trying to have a conversation. So where NBench came into the picture here is I invented it to put an end to this conversation before it drove me insane. So NBench was designed literally to settle an argument, is where this originally came from, about what is the real performance number of this feature of Akka.NET, and more importantly, how does each change in our software going forward affect this measure? So the idea was to go ahead and standardize our benchmark on one piece of code, measured with one instrumentation, measured on one machine. Our build server was going to be the single source of truth for this. That way, when people wanted to have a conversation about the performance, there was one authoritative place to get that data going forward. And so here's what the results of that looked like for us on the Akka.NET project. We started really recording our NBench performance data at the beginning of December. And you can see here, this is sort of the messages per second is what this graph is showing. You can see here on the left, we're sort of in this like 2400 range, right around there, as measured by NBench. And we see a little increase right here in the performance, a really tiny, minute one. That's because we found some inefficient thing we were doing with, I think, a string format call somewhere in there. So we fixed that. Tiny nudge in performance. Well, then one of our developers spent a week or two profiling some code and came to the conclusion that we had a contention issue in a custom thread pool implementation we were using. So he went ahead and rewrote that, and we had this big jump in performance, up to about 8,000 or 9,000 messages per second again. Big improvement, great. Then we had another incremental improvement here as a result of fixing something in our serialization system. And then this giant jump here was me screwing up the benchmark. So specifically, I designed it so the benchmark started counting its results before most of it finished running. So I fixed that, and then on top of that, because of the Windows Azure Marketplace doing something weird, our Visual Studio license on our build server expired, and I had to re-image it. So we sort of lost our performance baseline here, and it kind of jumped around a little bit, but then we sort of stabilized again. This is the most important part of the graph. What never happens there once we start measuring it? The performance never goes back down again. There's a saying, so I'm an entrepreneur in addition to a software engineer, and there's a saying sort of amongst people who are working in marketing at a startup company that if you can't measure it, you can't control it. If you aren't aware of sort of what your metrics look like as far as people using your product, you can't have a real conversation around what you need to do differently. The same is true for performance. By having this sort of history of our performance available for anyone to look at, we can have a real conversation on whether a given piece of change to our code was an improvement or not. It stopped being this sort of mysticism. Everyone knows that string builder is faster than appending strings together, right? Well, we decided to go ahead and basically use this NBench system as a way of talking about data rather than talking about theories. And then the performance continued to improve gradually over time, too. That's the other thing to notice. Once you sort of set a performance baseline, and you start testing against that, you'll find that your performance tends to always get better around the clock. So really, NBench was a tool that we wanted to use to sort of create a culture of measuring and testing against performance. So I look at performance testing as actually a type of defensive programming to some extent. What we want to try to avoid are sudden negative changes in the system. Memory consumption being one example. If someone changed the default queue implementation that we use in our mailbox in Akka.NET to be something that was much more memory expensive, that might mean that our customers who run Akka.NET on Xamarin Android or on embedded devices running Linux out in the field wouldn't work properly anymore. So we have to go ahead and basically protect against that. Throughput. That whole story I just told you was how we didn't do that, and it really pissed off some of our users. Never want to let that happen again. Garbage collection overhead. The number one enemy of sort of any high throughput application is going to be your garbage collector for the most part. And the reason is that when you need to go and collect those older generation objects, Gen 2 in particular, unless you have sort of asynchronous garbage collection turned on, that used to mean you'd have a pause across all your threads every 20 or 30 milliseconds. And that can actually make a real difference in some of your, in your total system throughput and also your total system reliability too. So this is something that we tend to keep an eye on. So these are the three metrics that in the akkanet project we really care about. Now, other things that other folks using NBench use, a lot of them care a lot about I/O. If you're developing a Xamarin application, you want to know how much bandwidth you're using, right? That makes a real impact on this experience your end users have. So you might want to keep an eye on how big your message sizes are going over the network. That'd be one example. Number of network calls. How many round trips does a request to a web API make to SQL Server every time you have to process it? If your entity framework, the answer is something really large. Sorry. Shared resource contention is another one. So one thing that some folks will try to track is for a given scenario, how many resources, how many different sort of threads or tasks are all trying to concurrently access the same thing. Contention overhead can be a real cost in a system. Quick show of hands. Who's ever had to debug a SQL Server lock contention issue in production before? Amen, brothers and sisters. So it's a real thing, real problem that we have to deal with. So this is where the concept of performance lifecycle management steps in. So the way I look at this is that for any given application, you have a set of performance constraints that you have to live in. This is determined by the environment in which your application runs. So quick show of hands, is a application running on someone's phone going to have different performance constraints than a big server-side application in Windows Azure? Who thinks so? Yeah, exactly, right? The environment is sort of what dictates a lot of those constraints. The other part of it might be the expectations you set with your users. How many of you run SaaS software as part of your work? Quick show of hands. A handful of you. Do you have service level agreements with your customers around turnaround time, availability, that sort of thing? Those might determine some of your constraints as well. Then the next part of the performance lifecycle is the notion of your performance critical path. Now, a little cautionary note about this. It's not always obvious. If you're building a Twitter application on Xamarin, your performance critical path might usually be the home screen where you're loading all the content. That's what people spend 90% of their time doing. But that doesn't mean that other parts of your application aren't on the performance critical path too. And I'll give you another embarrassing example from akkanet. So unfortunately, before we started using NBench, and even a little bit afterwards, the way we found out about performance problems was typically from our users. And one example was we had a situation occur where we made a change to our software, we published it, and we got a bug report back about 48 hours later saying it takes 10 minutes to shut down my actor system now. And so we started taking a look through it, and what turned out to be the case was we had a link statement that someone modified between patches that used to be lazily evaluated. Someone added a toList call at the very end of that, so it was fully evaluated on every request. So for a sufficiently large actor system, that became immensely expensive. So we had to go and change that back and come up with a better construct for it. Then we added an NBench test, and that's never happened again since. But the performance critical path can surprise you. So the way I'd sort of describe what's on the performance critical path, it's if a customer has ever yelled at you about it, it's on the path. Then you set targets against the path. 10 minutes for shutting down an actor system with 200,000 actors is not acceptable. We set a target a lot lower than that. 2 seconds was the number we picked. So we want to go ahead and make sure that we have a target that is sort of aligned with the expectations of our end users. So if you're working on a server-side application, a user might expect to get a response back from a web API you design in 500 milliseconds. That means that the components that are running inside that system have to execute faster than that, right? Considering all the other types of overhead you're supporting there. So you might go ahead and bound all the other subunits of your application underneath that one global target. Then here's the tricky part, measuring against the target. How do you determine if you've actually hit or missed the target or not? And then, in my opinion, the most important part of the performance lifecycle is maintaining what's called the performance history. This is a record of how your application has performed against its goals for every single patch. Every minor change, every pull request puts a new entry into the performance history. What this allows your team to do is produce a graph like the one I showed earlier, where you can go ahead and see how well your application's performed over time. And more importantly, it tells you who to yell at when your performance drops. So blame distribution is sort of solved by the performance history too. So for every regular update of your software, this would be a minor patch. Pull request would be a good example. You want to go ahead and run this process over again. Go ahead and measure against target, save it in the performance history. For any major version change of your software, you want to go ahead and run the entire process again. Reason for that? Well, reason why you'd presumably do a major version update is because there's significantly new pieces of functionality, or old pieces of functionality have been significantly rewritten. Or maybe you went ahead and added support for a new runtime you didn't have before. Great example that we're all dealing with in .NET, .NET right now is .NET Core. Our benchmarks that we had for .NET 4.5, 4.6 might be totally different than what they are for .NET Core. So we might have to set totally different targets that are aligned to what that platform can deliver. NBench belongs in this part of the sort of region here. It's designed to help you measure and also assert against your target, as well as update your performance history. So NBench is really designed to plug into your continuous integration system and allow you to continuously measure against your target and create a record of what your performance was for each change. And ideally, you want to do this before that change gets merged into your code base, not after the fact. Retrospective performance debugging isn't fun. So why is this hard? Why do people have such a hard, when we had this sort of argument within the Akka.NET team about what the cause of this problem was, what was the real challenge there? Why was it so difficult? Well, the first thing you have to think about when you start measuring performance is the fact that we're using a preemptive operating system. That means that you're going to have things like different schedules that happen while you're running a benchmark. So, for instance, Windows might go ahead and run one of my benchmark differently than run two, and I might see a divergent result there as a result of that. Virtual memory is another fun problem. You think you're allocating an object into memory when it's going to disk. That's going to show up in your total throughput measurements. Other processes are a bane of our existence too. I gave a version of this talk at .NET Fringe last month, and one of the things I did was I had two different NBench benchmarks. One was a stress test for Helios, the socket server that powers Akka.NET, where I had something like 700 open connections on one machine here. I had another benchmark trying to assess the performance of some simple function in Akka.NET. Well, the Akka.NET function ended up timing out and failing because the other process was using so much of the CPU. That's just something that can happen. Next is hardware variability. So cache pinning is a fun little exercise where, let's say, for instance, this is sort of a nuanced issue. You decide, okay, I want to go ahead and try to get rid of operating system unpredictability as a concern. So I'm going to do the smart thing and run multiple iterations of my benchmark and then average them all at the end. That way you can sort of average out some of the noise. Well, let's say you pick an even number for the number of iterations you're going to run. Well, all of a sudden the compiler and the CPU will get the smart idea to go ahead and do some loop unrolling and other stuff under the hood. And you'll end up in a scenario where your result is actually pretty skewed from what it would have been if you had picked a prime number instead. So that's sort of a little fun hardware variation you can deal with. But another issue is actually the generation of the chip itself. What if one machine you're benchmarking on has a newer generation Intel than another? It might have more L1, L2 cache available, and it might also have potentially different CISC optimizations built into it. Who here does work with floating point math in some part of their system? Quick show of hands. All right. Well, you might end up in a scenario where you benchmark on one machine where the .NET sort of just-in-time compiler is able to go ahead and take advantage of brand new x64 instructions for a new generation chipset. That'll produce a totally different result than what you get in an older machine that doesn't have those. Another fun one, runtime and dependencies. So the garbage collector, the JIT, or even just third-party modules you can depend on can actually impact your performance. One of my personal favorites was we had an issue where someone noticed that when they updated the version of, I want to say it was one of the serializers we support. I think it might have been JSON.NET, where they went ahead and upgraded that version of JSON.NET, which took into account some basic new ways of sort of representing objects and so forth, and our wire format actually got a lot bigger as a result of that. So just using sort of a new version of it. We ended up being able to sort it out and change some settings to smooth that out. But that's an example of a type of downstream change you may not expect, right? That's another reason why you want to measure those things. Keep an eye on how your third-party components are working too. Don't treat them like black boxes. Next is, this is actually kind of a subtle problem, how you gather the metrics. So these are platform dependent. Quick show of hands, who knows of a good cross-platform way of gathering performance metrics in .NET? Okay, the number of hands is 0, that's the correct number. The answer is not even it's very difficult to do today. If you're working on Windows, you have great options like performance counters and event tracing for Windows. On Linux, you kind of have stuff like being able to go ahead and collect the total amount of available memory from the garbage collector. That's sort of about it. Actually, instrumenting your specs can be challenging. The last bit here is that it's difficult to design isolated tests. So in particular, one thing you might have to do is be aware of when you need to go ahead and force some garbage collection to occur during different stages of your test run. And there's also potential background noise that can show up too, such as things, so the garbage collector is probably the worst source of this, but there might also be other resources that are being released in the background, et cetera. These are all things that make getting clean performance data tough. NBench is able to solve most of these problems, not all of them. I can't stop you guys from running your benchmarks on totally different pieces of hardware, but I can try to make it easier to get clean data. What NBench really offers is an API that feels a lot like writing a unit test. The real idea behind NBench is the concept of a performance specification. I'm going to go ahead and basically dictate that this piece of code is going to be able to execute n number of operations per second. And if that code ever falls below the expectation, we're going to scream loudly and fail the build during a pull request. That's exactly what I want as an open source maintainer. I want to go ahead and let my CI system tell me when someone's done something that adversely affects the performance. Because you know what? Even with a team of really good .NET engineers trying to review every pull request, how many of you think you can reliably spot a change that's going to have an impact on performance just by eyeballing it? I know I can't. I see the guys in particular shaking their heads. You know, it's definitely it's an issue where you really want to let your automation do that for you. Next thing that NBench does is it basically creates a record of your performance. We write the output of your performance specification to a file. That way you can go and review it later. And we also have some customizable outputs too. You can go ahead and basically write your output to a SQL Server database if you wanted to. Next is the data itself is collected reliably and it's believable when you take a look at it. So we have instrumentation built into NBench designed to go ahead and isolate the NBench process from other processes on Windows. We go ahead and adjust things like the thread priority and the actual process, the priority of the process too, to sort of ensure that the NBench process gets scheduled ahead of other things. These are just sort of common practices when you try to collect performance data. NBench is also fast. How useful would a benchmarking library be if it was slower than the thing it was benchmarking? Not very reliable, right? So NBench is designed to be fast. It's meant to be configurable. It's also meant to be extensible. NBench's systems can be extended to support alternative ways of gathering metrics. You can go ahead and extend it to basically write its output to different targets. We even had someone who just came up with a way of having NBench get hooked into the XUnit test runner in ReSharper. People have come up with some pretty clever stuff to do with it. And it's also open source. It's all licensed under Apache 2. And this is what an NBench Spec looks like. So this is one, I think I pulled this from, yeah, this is from akka.net actually. So I have this object up here called a counter. One thing that NBench was designed to do, so some folks might have asked me before about NBench versus something like benchmark.net. Who's heard of benchmark.net? Quick show of hands. So they've been using that on the .NET Core project to go ahead and measure the speeds of Kestrel and some of the other tooling that's coming out there. I use benchmark.net in my day-to-day work, and it's a really effective tool for micro-benchmarking. If you really want to precisely measure how many allocations or how much or how long it takes to execute, a million iterations of a particular function, benchmark.net will give you really precise results. One of the things that NBench does is it gives us the ability to go ahead and perform that sort of measurement for concurrent code, because it was designed for Akka.net, and it's meant to be concurrent itself. So these counters are thread safe. And then here I go ahead and have a counter name, and then I specify what's my boundary going to be. And I want to test, in this case, 1 million operations per second. I want to guarantee this parsing function can perform that. And I think right now it goes much faster than that, but still, that's like the minimum threshold we agreed on. Then I have a little setup method here where I basically go and allocate the counter in advance. One thing you never want to include in your benchmark is any of your setup overhead, for obvious reasons, right? The amount of time it takes you to instrument the test shouldn't impact the test itself. So that's why we treat those separately. So we get our counter, save its value up here, and then we have the actual benchmark specification itself. So I have this perf benchmark attribute. This basically tells the NBench runner that we have a performance specification here. And I'll go ahead and walk through what some of these settings mean in a little bit more detail. But then here's the really interesting part right here. We have our throughput assertion and our GC measurement. What our throughput assertion is basically saying is that for this counter's value, we expect at the end of this benchmark that the actual number of operations per second will be greater than whatever this value was. And I think I specified that at 1 million. So when I run this benchmark, we'll go ahead and see that the actual output of it will exceed this. And so this assertion will pass. Then I also have a GC measurement here. I'm just going to go ahead and record how many garbage collection events there are while the benchmark runs. And I'm also specifying this benchmark will run 13 times. We'll go ahead and allow it to run for about a second. And we're doing what's called a throughput benchmark. This means that what NBench will do is it'll estimate how many iterations of this function it'll take to last 1 second, and it'll use that as its baseline for this spec. And then the last bit here, this test mode equals measurement. This means that we're actually not triggering the assertions right now. Even though I have this counter throughput assertion attribute here, I'm not actually going to run the assertion. So there's going to be no pass-fail logic here. It's sort of a soft switch for turning that off. If I set this test mode back to assertion, it would run this assertion again. So that's what's going on there. So NBench is really about testing code against performance specifications. I want to go ahead and set a target for what I want to hit, and I want to get a pass-failed assertion back depending on whether we achieve that or not. Now what I'm going to go ahead and do here is I'm going to pull up a piece of code. I'm going to go ahead and switch here. All right. So I'm going to go ahead and open up my perf results folder. Let's see. Don't think I have a result yet. Okay, that's all right. I'm going to go ahead and actually run this Akka.net benchmark here. So let me go ahead and copy this real quick. There we go. Let me copy that. Go to here. So we're going to run the benchmark that I was showing on screen. All right. I'm going to go ahead and let that run for a moment. So I basically specified with the command line arguments, I wanted to skip a whole bunch of benchmarks that weren't really relevant here. So here what you can see on the screen is each iteration of the benchmark is going and basically counting how long it took to run, how many different iterations of the counter were there, and how many completed in under a second. All right. So this should finish in a couple of seconds here. All right, cool. And it looks like it has another spec that I caught in my regex. That's OK. Well, that's running. I'm going to go ahead and pull up my little NDC folder here. All right. Control-Shift-B. All right. OK. So we can go ahead and see the output that NBench produced right here. So if I scroll through it, you can see the fully qualified name of the performance method. You can see the human readable description I applied here, as well as some system information. So what's our processor count? What version of Windows are we using? What version of NBench? How many threads are there? That sort of thing. And then we get down to the data. So we can see here that based on our totals, we basically estimated that we could run about 597,000 iterations of this code in a second. That's using the very first warm-up that we generated. So one of the things that occurs during the warm-up is, remember how I mentioned earlier that we want to try to smooth out as much of the noise of the system as possible? What are a couple of things that can occur the very first time you run a benchmark that might throw off its numbers? Any guesses? How about the JIT compiler? You have to go and JIT the code the very first time you run it, right? So that's one piece of overhead that we try to smooth out by running a warm-up before we start doing the totals. What are a couple of other factors that might affect the benchmark? Disk. It's actually going and running loading the assembly, running it the first time. Yeah, that's one. Go ahead. Cache warming up, specifically cache pinning inside the CPU. We want to pin all the instructions for this function in there too. So a benchmark, what the NBench will do is it'll go ahead and actually run a number of warm-up sets to try to basically ensure the cache is pinned and to go ahead and basically start getting a cleaner signal for a read here. So you can see up top that we picked 597,000 operations during sort of the first part of our warm-up. But at the very bottom, you can see that my sort of per second totals down here are actually higher than that. That we're doing closer to 700,000 operations per second. Reason why that is because we actually did get the instructions cached. The jitter didn't need to do any additional work. And at this rate, the only thing really affecting the quality of our benchmark was the actual overhead of the function and anything else the operating system might have been doing in the background. Now, if I scroll down here and I take a look at the raw collections, you can see here the total number of garbage collection attempts for generation 0. So we're averaging, looks like 332 collections per run. The fact that number's pretty consistent across each of these runs probably means that it's we've sort of collected the right number. This is a pretty precise figure by the looks of it. For Gen 1, we could see we're not allocating any objects. Neither are we for Gen 2. So this is good. It means this function's not allocating long-lived objects. That's what we want. Then down here, we can see the parse results. So I can go ahead and see that we run the same number of times, but take a look at these values differing a little bit. You can see there's little deviations here. This is as a result of the preemptive operating system at work, where there might be other things that are getting scheduled under the same cores in the background. I'm running PowerPoint and a copy of Chrome and other stuff in the background. So there's lots of other processes that might be competing for some of those cycles. And where you can really see that show up a little bit is this value on the right, number of nanoseconds per operation. You can sort of see how that varies a little bit. We're all sort of in this range of about 1,450 nanos per operation, but there is some variation that occurs there. So what you want to do with any benchmark is don't worry about a single data point. You want to plot a line instead. So you want to care about the line on the graph, not an individual data point. And so we're not running any assertions here. So there's no sort of real pass or fail going on. Now, one thing I want to show, sort of an example of things that can affect the benchmark. Pull that back up. I'm going to go ahead and unplug my laptop. So it's in low power mode now. I'm going to run that benchmark again. And we'll see if the results are different this time, now that my laptop is running on battery power. OK. Operations per second still looks pretty good. We'll go ahead and have to see what the final results look like. Looks to me like it's running a little bit more slowly, but not by much. Because this isn't really a super I/O-intensive piece of code that's using a lot of different devices or peripherals in the computer. It's a fairly simple string parsing function, basically. The code that we're testing here is what we use to parse an akkanet actor address from a string. That's all that it's really doing. OK, looks like the operation sort of finished. So let me go ahead and pull up my code here again. And I can see that these files have different timestamps on it. So I think this is the one. 534. Yeah, this is it. All right, cool. So I'll go ahead and do Control-Shift-B again. Let me pull this up. So this is the second benchmark that we ran. Now, if we take a look at that, the average value here is 662,000 operations per second. Whereas here was 684,000 operations per second. So we're seeing a deviation of about 20,000 operations per second. Again, not very much, but what you'd expect given that the laptop is going to be running on a lower power mode when it's disconnected, right? That's an example of being able to produce a sort of reliable result under the circumstances there. So this is what NBench's instrumentation is designed to help you measure reliably, is the ability to go ahead and determine when your environment changes, when your dependencies change, when your code changes, what was the impact on the performance of this unit of code. So let me go back to my PowerPoint here. All right. Sorry about this. Okay. So NBench is all about testing code against its performance specifications. So some of the different types of benchmarks we offer, from a test mode point of view, we have measurement versus assertion. So the difference here is whether you get a pass-fail at the end when you go ahead and use some of those assertion attributes. And we also have the different run modes. There's the concept of an iteration mode, which I'm not using. The idea behind an iteration benchmark is, let's say you want to test a fairly large block of code, like an entire feature. You want to go ahead and benchmark how an entire feature works end to end. You typically set that up as an iteration benchmark, where you want to say, okay, I want to go ahead and run this benchmark that uses a fairly large piece of code 100 times and see what the final output is. And I'll pull up an example of one of those in a moment. So yeah, run n times. The other idea is this throughput benchmark, which is what we just did with that parsing function. These are designed for basically run a piece of code continuously for a fixed block of time. And what you want to do there is basically generate some load and measure like how well a very small unit of code worked. So this throughput benchmark is really for these like micro benchmark components. Iteration is really for these more macro, larger components. Now in terms of the things that we measure, throughput is one that you saw us use. How many things happened in a given second. Memory consumption is another thing that we can test. We use a fairly coarse-grained way of measuring that. We try to actually design NBench to be somewhat cross-platform, so it'll be easier to port to .NET Core. And we use the garbage collector for getting that number, which isn't as precise as what you can get using like event tracing for Windows or dot memory. But you can actually plug in different sort of memory consumption measures if you want. So the total number of bytes allocated is sort of what we measured today. Garbage collection, you saw us going and measuring collections per generation. So you can go ahead and basically write a benchmark where you can assert that gen 2 is always equal to 0 if you wanted to. That's a type of assertion we support. Elapsed time, this is end to end, how long did it take to do something? We have a benchmark in akka.net for testing against that long shutdown situation, where we go ahead and say the elapsed time for an actor system of this size to shut down must be under this number. We have that set up. And then we also have the support for some custom measures. So we have a performance counter plugin for NBench that allow you to go ahead and instrument any arbitrary performance counter against an NBench spec. So we've seen people use that for measuring things like total number of bytes transferred to SQL Server before. That's one example. So I already gave you a little demo. Now the next sort of big set of features that we're going to try to add to NBench down the road is the notion of an automated performance history, where NBench will output its history to some service, some web service somewhere, that'll be able to go ahead and ingest that data and give you a nice graph. But not rather than the one I had to construct from Excel before. This will go ahead and do that for you automatically on a web UI. Last thing I want to show real briefly is an iteration benchmark. So this is one of my favorites, and I don't think I'm going to run it because it will take like 10 minutes. That's not what I wanted to do. All right. This is what we use, and we have a version of this in NBench and another version in .NET, which are both sort of socket libraries in .NET. We call this a horizontal scaling specification. What we want to try to determine here, and actually let me scroll back up. What we want to try to determine with this benchmark is on a single machine, how many connections can we open before the throughput, on a single server before the throughput begins to drop. Now this benchmark isn't exactly fair because the client's workload and the server are both happening on the same machine, but it's to help give us an approximation for what the sort of resource overhead looks like. So we have sort of a client and a server bootstrap. We have a set of event loop groups for the client and the server. These are the different thread pools that are going to be running those workloads. And then we set up a few counters. We have a counter for the number of clients that have been able to connect, the inbound throughput, and the outbound throughput. And what we do here, we have a couple of setup functions. Set up our server and our client. Yep. Let me scroll down. Here we go. What this benchmark basically does is we go ahead and pick a random block of time that we want to choose, like 3 or 4 minutes. I think in the last version of this I did for .NET, which I don't think has been merged in yet, I think I picked a static amount of time for that. And what we do is you just go ahead and iterate over this loop, and we continue to basically just keep spawning clients that go and generate a continuous load. They'll go ahead and generate, I think, 10 messages per second each in the background. And this test on this little Surface Pro 4 here can generate about 850 open connections before we basically hit our maximum sort of timeout, which is that it took longer than 10 seconds to open 10 connections. We go ahead and sort of end the stress spec then. This is an example of something that's a little bit more like macro scale you can do with NBench too. And the merits of this are really there to determine sort of how much overhead goes into a client-server connection end-to-end. So that's the idea behind NBench. And what our goal with this project really is to allow you to go and plug in performance testing into your continuous integration system and have it as something your team continuously monitors in each pull request going forward. So that's it for sort of my prepared content. And I'll be happy to take some questions if you have any now. Thank you very much. Okay, do we have a microphone we can pass around? I think they're getting it. Okay, yeah, I'm back.
Okay, so
Microphone's coming. There we go.
So you were mentioning before about OS variability. Would that be mitigated somewhat if you were to run your application in a container?
If you're going to run your application in a container, those cores are still being, well, actually, let me rephrase. As long as you're able to pin one core to one container, meaning that nothing else could really schedule onto that, then that would mitigate that to some extent. However, if that core is still, if it like logically belongs to the container, but it's still really time shared across them, then it wouldn't make a difference at all. So that's also kind of a problem. One thing we do with Akka.NET's build farm right now, which is a bit of a problem, is we use auto scaling with Team City to go and dynamically allocate our build agents. Well, we've noticed that even though we're all using the same generation of Azure VMs, there's still significant variations in the values that we record in our benchmark. And there's 2 reasons for that. Even though they're all in the same generation, they can still have different hardware. But there's also the fact that we're running on a virtual machine. Who's to say we don't have a noisy neighbor who's sharing the same physical hardware that VM is on at any given time? One of my board members at my last company was a major AWS customer and noticed that they were having these horrible CPU starvation problems on their own system, even though their application wasn't under a huge amount of load. Turns out they were sharing the same boxes as Foursquare was. That's why they were having problems. Their time was being stolen by their neighbor, basically. So that's one example of where hypervisors and containers still don't necessarily give you the resource isolation they promise sometimes. So yeah, good question. You had one.
So at what stage in your ALM cycle do you normally perform these tests?
What stage in your ALM cycle do you want to start introducing performance tests? That's a good question. You know, I would say the quote that people throw out there about premature optimization is the root of all evil. There's actually like a second part of that I don't fully remember, but it's basically like you should still measure performance of your code anyway and try to improve it where you can. It's just that don't over-optimize things right away. I think you should introduce performance tests around the same time you start finishing features. When you have something that can be performance tested, you should start doing that. That way, at the very least, let's say the performance sucks for your very first generation. Well, that's okay. No one's using it yet, right? But when you start setting that baseline, you can see improvement over time. What it gives you is that sort of defensive programming means of never backsliding into bad performance again. So when you're at a stage where you're able to measure the performance of something, that's when I'd start trying to do that. As long as it's reasonably easy to do it.
Okay, because one caveat to perhaps the setting a scheduled time on these performance tests is that I can see fairly quickly that you might have a branch, and after your unit tests you might run your performance tests. But if you set a bunch of these to run, say for a minute or 2 minutes, these aggregate to these may aggregate to just running 5 minutes until it actually merges back into master or developer, whatever branch.
So you're talking about the length of the build process. Yeah, so here's a scary fact. Akka.net's end-to-end time to basically run a full build of the system, so we have 80 projects in our Visual Studio solution. And about a third of those are tests of some sort. So we have, I think, 3,000 to 4,000 unit tests, about 200 performance tests, and about 70 what are called distributed unit tests, where we actually go and simulate a network. If I ran the end-to-end build chain on my laptop here, it would take 90 minutes to execute. What we do on the build server is we actually go, this is a little bit more about CI than NBench. We actually go ahead and have different machines run each of those steps in parallel, is what we do. So that way I'm running the same 30-minute execution block in 3 places at once, right? So that's one way of doing it. Yeah, one thing you absolutely cannot do with a performance test is parallelize it. That's, for obvious reasons, that won't work. So you do end up having some extra time added to your build process for that. So what I would encourage your developers to do in that environment is maybe don't run all the performance tests locally for each step they do. Have a build server process that's designed to parallelize that work and just farm it out to that. That's what we do on the .NET and Akka.net projects too, is we let the build server do a lot of that work because it's just not productive for the developers to run it all the time locally anyway. So, yeah.
Hi there, how you doing?
Hello, good.
Are you really?
Yeah.
Okay, I've got 2 questions. First one is around downstream dependencies. Talk to me about those.
They're the worst, avoid them.
Yeah, I get that.
I'm just kidding. With downstream dependencies.
Welcome to the real world though.
In the real world with downstream dependencies, here's what I really mean. Particularly with major versions of downstream dependencies, you got to go ahead and basically say, okay, is this downstream dependency in a performance critical path? Great example of that in Akka.net is our serializers that we depend on. With the remoting pipeline and also the persistence system that we use for saving events, the serialization system sits in the middle of that. So the impact, the speed of our serializer will affect the speed of our remoting system. So we're in the process of switching from JSON.NET to Wire right now in Akka.net. Wire is about 25 times faster than JSON.NET, and that shows up in the benchmark big time. So what you want to do is just have a measurement set up so you can witness the impact of that. It just gives you visibility into it as a team. So that's the sort of high level part of that. Does that answer your question?
Yes, that's one part of my first question. What about anything that has to across the network? Do you ever use this to hit network, like external systems, and kind of test them?
Yes, I've used this to hit like SQL Azure databases before.
Yep.
So I had some performance test an entity framework application at one point, and one of the things I was paying attention to was my elapsed time. End to end, how long did it take for me to complete a full cycle of one request?
Yep.
And so I used NBench there to go ahead and basically just get a measurement of that. And the other thing I measured was I used a performance counter to see how much traffic was going onto the network during this part too. So I wanted to get a sense for, okay, if I have a pipe between here and SQL Azure that can handle n number of bytes, and Windows Azure is well designed, it can handle a lot, but still I wanted to know what's the upper limit of this system. I want to go ahead and see, okay, how much is, when we go ahead and run this one web method of this web API that was developed, what's the total amount of bandwidth it uses? So I'd go ahead and measure that. Those benchmarks will take a while because they depend on external network calls, but they're still worth doing. So yeah, not all benchmarks need to be running a function hundreds of thousands of times to see how quickly it turns, right?
Okay.
That's the idea of those iteration benchmarks that basically are bigger blocks of code that take longer to run.
Okay, cool.
Yep.
Second question is, can you catch?
Can I catch?
Yeah.
Not very well.
Yes.
Well enough. Well done. Commonwealth Bank. All right. Thank you. Next question. Sergey.
First of all, great work. And I forgot who said that. If you don't measure what you do, you're not an engineer.
Yeah.
Like you proved that. I'm curious if you ever measure the impact of hyperthreading.
Measure the impact of hyperthreading. No, that's an interesting one. When we actually go ahead and take a look at that core count in the sort of report up there, it's the number of logical CPUs, right? So for every sort of Intel-based processor, that's going to show up, that has hyperthreading in it, that's going to show up as 2. I don't have a measurement right now for breaking that down, where it's like, what's the impact of having things scheduled under the same hyper-threaded CPU, right? So no, I haven't done that. That'd be interesting though. I actually don't know.
We looked at it a while ago, and it was very negative. So we turned it off and never measured after that.
You turned hyper-threading off?
Yes.
Oh, that's good to know. I should take a look at that. One thing I have a pull request that's open for this on NBench right now, but we have one of the things we're going to make more extensible. You saw that list of information about the system is pretty basic right now. What we're going to do is we have a system that queries WMI and pulls a much more detailed fingerprint of your system. Being able to see what generation of processor you're using, is hyperthreading turned on, and maybe some other important settings too, like what's the size of the virtual page file. I'm just throwing that out there as an example. These would be interesting things to know potentially, and sort of getting a more complete benchmark. Another thing I've seen folks, particularly at the benchmark.net project, do is experiment with what's the performance of your application with different JIT configurations, comparing classic versus Ryu JIT, for instance. They'll also go ahead and test things like x86 versus x64. Now, if you've got a piece of code that doesn't align to a 32-bit cache, you're going to see a noticeable performance difference there. So those are all things that I think, in terms of what NBench scratches the surface of today, there's a lot more work to be done there in terms of getting that much more detailed metrics about different system configurations and the impact they can have. Cool. Yes?
So I was wondering if you thought this might be a good context for NBench. At my company, global company, we've got a lot of jobs that users run, and the jobs can take anywhere from 3 seconds to 10 minutes. And some of them are very time sensitive. Obviously, I'm talking outside the build pipeline, but do you think NBench would be good perhaps nightly or weekly, kind of running through hours and hours of these, like running each job once just to kind of get that historical graph of time? Because that seems like it'd be really useful.
Yeah, absolutely. Being able to use, so basically having like a cron job that runs NBench, and like using the elapsed time measurement might be a good one. So when we run this job, what was the end-to-end processing time for that? Being able to go ahead and see a trend line where, let's say, you're able to produce consistent results over time for the same job, that's good. But what happens if you see a big dip in processing time? Will that be something that would indicate that maybe there's something up with that customer's account if it's a data-driven thing? Or maybe the piece of code that job is running has changed in some way. So yeah, that'd be a useful thing to do, absolutely. Any other questions? Wire was the name of it. So it's if you go to akka.net on GitHub/wire, you can see that there. They're currently working on .NET Core support for it. Yep, WIRE. Yep. We like picking names for open source projects that aren't easily Googleable. That's how you know. All right, any other questions? All right, thank you very much.